The tremor in Oberingenieur Klaus Hermann's fingers was barely perceptible as he worked the screwdriver into the sealed edges of the metal case. Inside that steel container lay a captured American radio set, and gathered around the underground laboratory in Tunis were 5 of Germany's most accomplished radio engineers. They had pulled this equipment from the wreckage of the fighting at Kasserine Pass just 2 days earlier, and now they were about to uncover a truth that would shake the foundations of everything Berlin had told them about American capability. For 3 years, the propaganda had been relentless. American technology was mass-produced garbage, they'd been told, inferior designs churned out by assembly line workers in a nation of shopkeepers. The Reich's Radio Intelligence Service, the Funkabwehr, had reported again and again that Allied forces operated with outdated equipment and poorly trained personnel. Yet something didn't add up. The Allies maintained flawless communication across vast distances. Their fleets never lost contact with each other. Ground units coordinated with a precision that suggested far more sophistication than any primitive radio system should allow. Hermann's hands steadied as the case opened. Before him lay the SCR-508, a standard American tank radio recovered intact from a Sherman tank destroyed in the Tunisian mountains. What his team would discover in the next 72 hours would obliterate every assumption the German military held about American industrial power and technical sophistication. The mathematics of radio communications were about to reveal something far worse than any battlefield defeat, something written into frequency crystals and manufacturing processes that Germany could never hope to match. The captured equipment had begun its journey to Tunis just 2 days earlier. On February 14th, during Rommel's desperate counterattack at Kasserine Pass, German forces had achieved a tactical victory against inexperienced American troops. The American Second Corps had been pushed back 50 miles, and over 100 tanks lay destroyed in the desert. German technical intelligence teams moved swiftly through the wreckage, searching for weapons and documents and any equipment that might reveal Allied capabilities. Hauptmann Friedrich Weber commanded a signals intelligence detachment attached to the 21st Panzer Division, and he had standing orders to capture American radio equipment in working condition. In a crater east of the pass, his team discovered an abandoned Sherman tank, its turret blown completely off by an 88mm gun, but the radio compartment somehow untouched by the blast. Inside that small space, Weber found not one complete radio set, but 2. The SCR-508 designed for tank-to-tank communication and an SCR-510 receiver. Both remained intact, their crystals and cables and technical manuals all secured exactly in place. Weber knew immediately what he had found. He ordered the equipment transported to the nearest technical facility, understanding that this discovery could yield invaluable intelligence about how the Americans maintained their communications network. The radios arrived at Technical Testing Station 12 on February 16th. The facility occupied an underground complex hidden beneath Tunis, housing Germany's finest radio engineers, men who had designed the Wehrmacht's own communication systems. Oberingenieur Klaus Hermann, former chief designer at Telefunken, would lead the examination. With him were specialists in frequency generation, circuit design, manufacturing processes, and signals intelligence. They began with what should have been a simple external inspection. The American radios were enclosed in heavy-gauge steel cases, painted in olive drab, with rubber gaskets sealing every connection point. Hermann noted in his first observations that the construction quality surpassed anything he'd encountered in German military equipment. These cases had been engineered to withstand water and dust and shock and temperature extremes that would demolish most German radios. But the real shock came when they opened those cases. Everything inside was standardized. Every component matched the specifications in the accompanying manuals. There were no hand adjustments, no technician markings indicating individual tuning, no variations requiring skilled hands during assembly. This was equipment designed to be manufactured by the millions by semi-skilled workers in factories that could be replicated across an entire continent. Lieutenant Hans Schreiber, a specialist in frequency control systems, examined the crystal units that governed the radio's operating frequencies. He had anticipated finding simple, inexpensive crystals, perhaps even salvaged civilian components. Instead, he held precision quartz crystal oscillators, each one ground to tolerances measured in parts per million, hermetically sealed in metal holders with specifications that would have demanded weeks of laboratory work in Germany. The SCR-508 contained 10 crystal-controlled channels, each crystal individually packaged and interchangeable and marked with exact frequency designations. Schreiber counted the crystals twice, unable to accept what he was seeing. In Germany, crystal-controlled radios existed only in high command units and aircraft, where the enormous expense and scarcity of precision crystals could be justified. Here, in a standard American tank radio, 10 crystals had been installed as casually as light bulbs. He carefully extracted one crystal and examined it under magnification. The quartz gleamed flawlessly. The electrodes were perfectly aligned. The frequency marked with absolute precision. This single crystal would have cost more than an entire German FUG-5 radio set in materials and labor. Yet the Americans had installed 10 of them in every tank radio, and they had already produced thousands of Sherman tanks. The initial examination revealed increasingly disturbing discoveries. The radio operated on frequency modulation, FM, rather than the amplitude modulation, AM, that German radios employed. Theoretically, FM was superior, delivering static-free communication and resistance to interference, but it required significantly more complex circuits and precise frequency control. German engineers had considered FM for military applications, but rejected it as prohibitively expensive and complicated for field use. Yet here was an FM radio, mass-produced, installed in a tank driven by junior American soldiers. The circuit boards contained automatic frequency control circuits that kept the radio locked on frequency without continuous manual adjustment. German radios demanded that operators constantly retune to compensate for temperature drift and component aging and power supply variations. American radios, it appeared, tuned themselves. Hermann began drafting his first report to Wehrmacht High Command in Berlin, and the words came with difficulty. Each sentence contradicted years of propaganda and official intelligence assessments. He wrote that the captured American radio represented industrial sophistication that Germany could not replicate. The components were manufactured with precision that required specialized factories and trained workers, and quality control systems that simply did not exist in the Reich. More alarming still, the radio was clearly not a prototype or limited production model. Every design element screamed mass manufacture. The Americans were producing these radios by the thousands. Over the following 3 days, the team systematically tested every function of the captured equipment. They connected the radios to power supplies and antenna systems and test instruments that filled the underground laboratory. Each test deepened their growing sense of dread. The SCR-508's transmitter generated 25 watts of clean FM signal on any of 10 selectable channels. The switching mechanism that selected channels was elegant and reliable and required no technical knowledge to operate. A tank commander simply rotated a knob to select a preset crystal, and the radio automatically switched frequencies and retuned its circuits and maintained perfect transmission quality. In German radios, changing frequencies required a trained operator to manually adjust multiple controls, replace coils, and spend several minutes retuning. Range tests proved even more disturbing. Using a captured American whip antenna, the team established contact with a monitoring station 20 kilometers away. The FM signal arrived clearly, without the static and fading and interference that plagued German AM communications. Even when they deliberately introduced electrical noise from a tank engine, the FM receiver's limiting circuits stripped away the interference, delivering clean audio that German operators could only imagine. Lieutenant Schreiber focused his examination on the crystal oscillator circuits, tracing every component and measuring every voltage, and documenting the design with meticulous precision. What he discovered confirmed his deepest fears. The crystal control system was not simply sophisticated. It was impossible to duplicate with German manufacturing capabilities. Each crystal oscillator required a precisely cut quartz plate, ground to specific dimensions, measured in thousandths of a millimeter. The crystals were then mounted in evacuated or gas-filled holders, with electrode spacing controlled to tolerances that German factories could not achieve in mass production. Temperature compensation circuits maintained frequency stability across operating temperatures from -40 to +60 degrees Celsius. Schreiber calculated that producing a single crystal to American specifications would require approximately 40 hours of skilled technician time in German laboratories. The Americans had installed 10 such crystals in each tank radio. With thousands of Sherman tanks already produced and similar radios installed in American Jeeps and trucks and command vehicles, the Americans were manufacturing millions of precision crystals annually. He posed the obvious question in his report. Where were the Americans obtaining enough trained technicians to produce millions of precision radio crystals? The answer, when it came from intelligence sources, proved even more disturbing. The Americans were not employing highly trained technicians. They had industrialized the entire process. New factories in cities like Chicago and New York and Fort Wayne employed thousands of semi-skilled workers, predominantly women, operating specialized grinding machines that produced crystals automatically. Precision measurements were performed by optical comparators and frequency counters, not by skilled technicians. Quality control operated on statistical principles, with random samples tested rather than individual inspection. The Americans had transformed a laboratory art into an industrial assembly process. The examination of the radio's receiver section revealed even more advanced technology. The superheterodyne circuit design resembled German receivers, but the components were superior in every measurable aspect. Vacuum tubes were manufactured to tighter tolerances, with characteristics precisely matched to circuit requirements. Capacitors and resistors possessed stability ratings that German components could not achieve. The entire receiver had been designed for alignment by semi-skilled technicians using simple test equipment, rather than requiring radio engineers with years of training. Most disturbing was the modular construction. Every major subsystem, transmitter, receiver, power supply, and control unit, was a separate replaceable module. A tank crew could remove a failed unit and install a replacement in minutes, without tools or technical knowledge. Damaged modules would be returned to depot facilities for repair or disposal. This approach demanded massive industrial capacity to produce spare modules, but it ensured that American tanks maintained communications capability under conditions that would leave German vehicles radio silent for days while technicians performed field repairs. The team examined the technical manuals accompanying the radios. These documents, printed on high-quality paper with clear diagrams and straightforward instructions, assumed that operators possessed minimal technical training. Operating procedures had been reduced to numbered steps. Troubleshooting guides used decision trees that any soldier could follow. Maintenance instructions specified exact replacement intervals for components, rather than relying on operator judgment. Herman realized that these manuals revealed as much about American industrial philosophy as the radios themselves. The Americans had accepted that frontline soldiers were not technicians. Rather than train every radio operator to understand electronics, they had engineered equipment that any reasonably intelligent soldier could operate and maintain using simple procedures. This required more sophisticated equipment, but it solved the fundamental military problem of maintaining communications under combat conditions. German radios, by contrast, required skilled operators who understood radio theory, could perform field repairs, and possessed the technical judgment to maintain temperamental equipment. These operators required months of training and years of experience. They represented irreplaceable assets, and when they were killed or wounded, their equipment frequently became useless to whoever inherited it. By the end of the third day, the examination team had documented every circuit and measured every component and tested every function of the captured American radios. Their report to Wehrmacht High Command exceeded 200 pages of technical analysis, supported by photographs and circuit diagrams and component specifications. The conclusions devastated anyone who read them carefully. The Americans possessed radio technology that was 5 to 10 years ahead of German equipment in critical areas. Frequency modulation, crystal control, automatic frequency circuits, and modular construction represented fundamental advantages that could not be overcome by superior tactics or operator skill. More critically, American radio equipment had been designed from inception for mass production. Every aspect of the design reflected an industrial philosophy that Germany simply did not possess. Hermann's report estimated that Germany would need to construct 30 new specialized factories and train 50,000 additional workers, and invest resources equivalent to the entire annual Luftwaffe budget to match American radio production capabilities. Even then, Germany lacked the raw materials, particularly high-quality quartz crystals and certain rare elements needed for precision components. The conclusion was inescapable. American industrial capacity had made technological superiority militarily decisive. The report reached Berlin on February 25th. It was classified most secret and distributed only to a handful of senior officers in Wehrmacht High Command and the Reich Ministry of Armaments. The response was silence. No new factories were authorized. No crash programs were initiated. The implications were too devastating to acknowledge. But the work at Technical Testing Station 12 was only beginning. Over the following months, more American equipment fell into German hands. Each capture provided fresh evidence of American technical and industrial superiority. An SCR-300 radio, the famous backpack walkie-talkie, revealed FM technology miniaturized into a portable unit that weighed only 18 pounds, yet provided reliable communications up to 5 kilometers. German portable radios of comparable range weighed over 40 pounds and required external battery packs that added another 20 pounds to the operator's burden. An SCR-299, captured in Sicily in July 1943, stunned the examination team entirely. This was a mobile long-range communication station installed in a truck with an integrated power generator, capable of transmitting thousands of kilometers with perfect clarity. The transmitter cranked out 350 watts across frequencies spanning from 2 to 18 megahertz, with crystal control that held steady and the flexibility to shift frequencies in mere minutes rather than days of fiddling. Paired with this was the SX-28 receiver, a sophisticated helicopter companion built on super-heterodyne principles. 15 vacuum tubes handled multiple conversion stages, while a crystal filter sharpened selectivity to remarkable precision. Germany had long-range communications gear with comparable specs, sure enough. But there was a catch. Those systems only worked from fixed installations demanding massive antenna arrays and dedicated electrical power plants. The Americans had compressed equivalent capability into something revolutionary, a vehicle that could roll anywhere and operate within an hour of arrival. Every piece they examined told the same story. American design philosophy centered on simplicity. Minimally trained users could operate the equipment. Semi-skilled factory workers could mass-produce it. Maintenance followed straightforward procedures that almost anyone could manage. German philosophy demanded the opposite. They built equipment for skilled operators, hand-assembled by trained technicians, serviced in the field by specialists with deep electronics knowledge. One approach scaled to millions of units worldwide. The other simply didn't. Technical intelligence flowing back from Tunisia, Sicily, and up through Italy revealed something larger than individual radio sets. It exposed an entire communications philosophy. American forces maintained constant conversation from squad level all the way to theater command, woven through multiple overlapping radio networks that created unprecedented coordination. Squads carried SCR-536 handheld units. Companies deployed SCR-300 backpack systems. Battalions fielded vehicle-mounted SCR-508 and 608 equipment. Regiments operated with SCR-193 and 299 long-range sets. Each command level could speak to those above and below, forming a connectivity web that German forces simply couldn't replicate. Critically, every American radio spoke the same frequency language. The systems were compatible throughout. A forward observer with an SCR-300 could reach an artillery battalion 20 kilometers distant on an SCR-608 because both used FM on identical frequencies with crystal precision. German forces operated in fragmented chaos, multiple incompatible systems, each demanding different frequencies, different modulation approaches, different procedures entirely. By summer 1943, German signals intelligence had catalogued more than 50 distinct American military radio types, from handheld transceivers to airborne command systems. Production figures drawn from captured serial numbers and intelligence suggested American factories pumped out over 100,000 military radios monthly. German production, counting all services combined, maxed at roughly 15,000 units per month. The examination teams dove into captured American manufacturing documentation with growing alarm. Technical orders, component lists, and service manuals showed the machine behind it all. Parts were standardized. Vacuum tubes used uniform base configurations. Crystals fit standard holders. Even screws and bolts followed unified thread standards that meant parts were interchangeable. This meant American plants could shift production between different radio models without massive retooling. A factory building SCR-508 transmitters could convert to SCR-608 production by swapping a few fixtures and component types. Components salvaged from one radio often repaired another. The whole system breathed flexibility and scalability. German manufacturing operated differently. The FUG-5 tank radio shared almost nothing with the FUG-10 aircraft radio, despite performing similar electrical functions. Each required dedicated production lines, unique test equipment, specialized spare parts warehouses. Changing production meant months of equipment overhaul and worker retraining. Oberingenieur Hermann transferred to a larger technical intelligence facility in northern Italy as autumn 1943 set in. His focus shifted progressively from pure equipment design toward American manufacturing methods. His reports to Berlin transformed from circuit analysis into stark strategic warnings about industrial might. He documented the American electronics industry's explosive expansion. Companies like Galvin Manufacturing, later Motorola, shifted from small radio makers into colossal military suppliers. Hallicrafters, once producing amateur radio gear, now manufactured sophisticated military receivers in quantities exceeding Germany's total radio output. Western Electric, the manufacturing division of Bell Telephone, operated factories with tens of thousands of workers, churning out crystals, vacuum tubes, and complete radio systems. None of these firms existed as major military contractors before 1941. America had conjured an entire military electronics industry in under 2 years by converting civilian facilities, training new workforces, and borrowing mass production techniques perfected in automobile and appliance manufacturing. Detroit's automotive engineers designed radio assembly lines operating with car plant efficiency. The German radio industry, centered in Berlin, Munich, and Hamburg, remained organized as it had been in the 1920s. Small manufacturers produced specialized gear using skilled craftsmen. Monthly output was measured in hundreds, not thousands per week. Quality control meant individual inspection and hand adjustment, not statistical process monitoring and automated testing. Hermann's December 1943 report to the Reich Ministry of Armaments carried the title The American Radio Industry and analyzed industrial capacity and strategic consequences. The assessment documented American electronics production with chilling precision. United States factories produced annually what would require Germany 2 decades to manufacture. The gap transcended technology alone. It was industrial, organizational, and philosophical. The report projected American factories could equip 1,000 divisions with radios, though American forces fielded roughly 90 divisions. That excess capacity meant American soldiers had unlimited replacement equipment. Broken radios got swapped, not fixed in field tents. Obsolete models cycled to training units. Fresh designs rolled out continuously, not as experimental prototypes, but as mass-produced equipment deployed across entire theaters. German forces guarded every radio jealously. Field technicians performed repairs while bullets flew, cannibalizing damaged sets to keep others running. Replacement equipment arrived sporadically or not at all. New designs stayed in limited production because retooling would undercut existing output. Wehrmacht operators managed radios from the early 1930s alongside newer equipment, creating nightmares for maintenance and training. Crystal supply became a crisis point. By late 1943, German quartermaster estimates showed 5 million precision crystals needed for existing radios plus planned improvements. Domestic capacity produced roughly 200,000 crystals yearly. Even with enormous resources devoted to crystal expansion, a decade of production wouldn't yield 5 million units. Americans, according to intelligence, produced 30 million crystals annually. They'd tackled quartz supplies by discovering Brazilian deposits, mining operations in Arkansas, and experimental synthetic crystal cultivation. American crystals weren't just plentiful, they achieved frequency stability. German laboratories struggled to measure, much less replicate. Examining captured American test equipment revealed another industrial gulf. American radio factories deployed automated testers measuring frequency, power output, modulation quality, and sensitivity in seconds. These instruments themselves were sophisticated electronic gear produced in such quantity that every assembly station possessed dedicated test capability. German plants relied on manual procedures demanding skilled technicians and minutes per unit. One captured instrument, a Measurements Corporation signal generator, became a prized acquisition for the technical facility. This standard American factory tool could produce precisely calibrated signals across the entire radio frequency spectrum. Manufacturing cost was roughly $300. The German equivalent required a room full of separate oscillators, attenuators, and frequency measuring devices, costing thousands of Reichsmarks and demanding constant engineer calibration. By early 1944, technical intelligence delivered a message both clear and terrifying. American communications superiority was absolute, irreversible, and accelerating. Monthly production dwarfed Germany's entire military radio inventory. Every captured example displayed incremental advances, design refinements, and manufacturing precision beyond German capacity. The appearance of American radar systems in late 1943 and early 1944 hammered the point home with even greater force. Radar represented radio technology pushed to its extremes, employing microwave frequencies, pulse generation, and complex signal processing. The Americans mass-produced radar sets for ships, aircraft, and ground stations with identical industrial efficiency they applied to voice radios. A captured SCR-584 fire control radar, examined in March 1944, demonstrated technical performance German radar scientists had only theorized. Operating at the extreme frequency of 3,000 MHz, it used precision tracking mounts with automatic follow circuits, achieving accuracy enabling anti-aircraft guns to destroy enemy aircraft with devastating precision. The SCR-584 weighed over 10,000 pounds and required dedicated transport. Yet American factories produced them by the hundreds. German radar development pursued long-wave systems below 1,000 MHz because German industry lacked capacity for specialized tubes operating at higher frequencies. The magnetron tubes powering American microwave radar demanded precision machining, exotic materials, and manufacturing expertise Germany simply didn't possess. When German scientists designed microwave radar on paper, construction proved impossible. Necessary components didn't exist in German industry. Systematic examination of captured American equipment continued through 1944 as Allied forces pushed up the Italian peninsula and prepared the France invasion. Each new discovery stacked more evidence of American technical dominance. Enhanced radios appeared regularly. The SCR-694, introduced mid-1944, provided FM tank communication with increased range and reliability. The SCR-619 aircraft radio offered hundreds of crystal-controlled channels and instantaneous frequency shifting. Most significantly, American equipment reliability climbed continuously. Early SCR-300 units sometimes suffered moisture ingress and battery contact problems. Late 1944 examples showed redesigned housings, improved sealing, and modified circuitry solving these issues. Americans weren't simply building, they continuously refined designs through combat experience and field feedback, incorporating improvements into ongoing manufacture. German equipment often deteriorated as war progressed. Material scarcity forced substitution of inferior components. Skilled workers got drafted into combat, replaced by inexperienced personnel. Quality control slipped as factories prioritized quantity over dependability. Radios that should have functioned for years failed after months. When D-Day arrived in June 1944, German technical intelligence possessed complete understanding of American communication superiority. Allied forces landing carried more radios than Germany's entire army owned. Every Allied company maintained radio contact with battalion headquarters. Every battalion reached division command. Artillery observers directed fire from dozens of kilometers away with perfect precision because radios never lost signal. German commanders attempting to coordinate defensive operations watched their communications collapse under Allied jamming, artillery fire, and battle's chaos. Radios perfect on test ranges failed in combat. Crystal oscillators drifted frequency in Norman summer heat, severing unit contact. Battery-powered sets depleted rapidly, with no replacement batteries available. The communications network German doctrine depended upon simply disintegrated under combat pressure. Technical reports returning to Berlin grew increasingly frantic in tone. By August 1944, Hermann, now attached to Wehrmacht operations staff, reported Germany had already forfeited the electronic war. American jamming equipment, direction-finding systems, and signal intelligence capabilities allowed Allies to locate and target any German transmission within minutes. German codes lay broken, frequencies monitored, movements tracked through radio traffic analysis. Final collapse arrived late 1944 and early 1945 as Germany's industrial base crumbled under Allied bombing. Radio manufacturing facilities became priority targets. Telefunken's Berlin plants fell in November 1944. Lorenz production facilities in Stuttgart faced repeated bombing. The Crystal production plant in Sudetenland fell to Soviet forces in January 1945. By March 1945, German radio production had essentially stopped. Existing equipment continued functioning, maintained by increasingly desperate field technicians, cannibalizing parts from damaged sets and improvising repairs with whatever materials lay at hand. Replacement radios simply weren't available. When a headquarters radio failed, commanders lost contact with units. When tank radios broke down, armored formations became isolated vehicle groups incapable of coordinated action. Americans, meanwhile, kept enhancing equipment as victory approached. New radios introduced early 1945 boasted extended range, more channels, and improved dependability. Production proceeded at full capacity, not from tactical necessity, but because the industrial machine couldn't easily halt. By May 1945, American supply depots overflowed with surplus radio equipment destined never to see combat. Unconditional German surrender arrived May 8, 1945, ending the conflict in Europe. Imagine opening a box filled with captured equipment and discovering your enemy's secrets. That's exactly what happened when German technical experts began cataloging American military devices seized from battlefields across Tunisia, Sicily, and Italy. These documents, stamped with the highest security classifications by Berlin authorities and locked away in underground vaults, handed Allied investigators something unexpected after the war ended. They could finally read what German specialists honestly thought about American technology. When American technical teams swept through German facilities in the summer of 1945, they made a startling discovery. The Germans had examined American radios with meticulous care. Every report was accurate, thorough, and professionally written. These weren't propaganda exercises or dismissive critiques. The Germans had candidly identified American technical strengths and frankly admitted their own limitations. One report stands out from all the rest. Oberingenieur Klaus Hermann wrote it in April 1945 as Soviet forces tightened their grip around Berlin. For Hermann, it became his final statement on the technological war between the two nations. Hermann's conclusion was stark and unambiguous. Germany's fate was sealed the moment German engineers cracked open that first captured American radio in Tunisia. What they found inside changed everything they thought they knew about warfare. The frequency crystals, the automatic circuits, the modular construction, all of it revealed something terrifying. The Americans hadn't just built better equipment. They'd industrialized warfare itself, turning mass production techniques into weapons. He understood something fundamental that German leadership seemed to miss. Future conflicts wouldn't be decided by superior soldiers or brilliant tactics. They'd be won by whichever side could manufacture advanced technology in staggering quantities. Germany had excellent fighting men and capable commanders. German tactics were sound. But Germany lacked something America possessed in abundance: the industrial foundation to match American production output. The most telling example was something remarkably simple: a radio crystal, perfectly round, finished to exact measurements by teenage factory workers in plants that churned out millions annually. Meanwhile, German laboratories struggled just to produce thousands. That gap told the entire story. What happened to these German engineers after the war revealed just how completely the world had shifted. Klaus Hermann caught the attention of American intelligence officials in 1946. They recruited him to spend 2 years detailing everything he knew about German radio technology. Later, he became a consultant helping American electronics firms understand which German techniques might be worth salvaging and improving. His colleagues followed similar paths. Operation Paperclip and related programs systematized this brain drain, bringing thousands of German scientists and engineers to America. They brought technical knowledge, certainly, but what they really learned were American industrial methods, mass production strategies, and the organizational thinking that made American victory inevitable. They witnessed firsthand how American companies built and scaled operations. By 1952, Hermann had distilled years of wartime observations into a technical paper published in the Institute of Radio Engineers Proceedings. The title was straightforward, describing a comparative analysis of German and American military radio design from 1939 to 1945. Hermann explained the fundamental difference in design philosophy. American radios prioritized ease of manufacturing, operational simplicity, and rock-solid reliability above all else. Sophistication and component efficiency mattered less. German design chased technical perfection and theoretical elegance, banking on the fact that skilled operators could work around equipment limitations. One approach multiplied across millions of units deployed worldwide. The other simply couldn't scale. The paper became standard reading in engineering programs and military academies. An entire generation of American engineers designing Cold War systems, space hardware, and early computers learned from his analysis. These lessons rippled through decades of technological development and shaped American engineering dominance. By the 1980s, the surviving German technicians who'd worked in technical intelligence during the war began gathering at reunions and conferences. They shared stories, compared memories, and reflected on what they'd witnessed. Hermann, now in his 70s, gave presentations describing his work, examining those first American radios in Tunisia and Italy. At a Munich conference in 1986, he displayed photographs from February 1943, showing young German engineers clustered around an opened radio chassis. They were measuring circuits, carefully documenting every component, struggling to comprehend the sophistication in front of them. Hermann told his audience that the moment they removed the crystal holder and saw 10 precision oscillators installed in what was supposed to be a basic tank radio, he knew the outcome was already decided. That tiny quartz wafer, ground to exact specifications and sealed in metal, represented something profound. It wasn't complex in concept. Any capable laboratory could manufacture one. But producing millions, all to identical standards, all perfectly interchangeable, all cheap enough to install in every military radio, required industrial capabilities Germany simply didn't possess. America built that industrial infrastructure between 1941 and 1945. When peace came, it didn't disappear. It evolved and expanded, manufacturing transistors, integrated circuits, microprocessors, and eventually the computers and communication systems that built the modern world. The same factories that had mass-produced radio crystals for Sherman tanks later mass-produced semiconductors for space vehicles, chips for home computers, and components enabling global telecommunications. The foundational principles became embedded in how America approached manufacturing. Design everything for production efficiency. Use standardized components. Train operators for simplicity, build quality into every step, test thoroughly, scale production to meet demand. These weren't abstract concepts anymore. They were visible in every American radio during World War II. and they became the standard methodology for every high-tech industry that followed. In 1995, marking 50 years since the war's end, the Smithsonian Institution unveiled an exhibition titled Communications and Victory, The Radio War, 1939 to 1945. Visitors could examine an SCR-508 tank radio. The serial number matched the exact unit Oberingenieur Hermann's team had studied in Tunisia back in February 1943. German archives had preserved it, and a cultural exchange program had brought it home to America. Beside the radio sat translated excerpts from German technical reports. Visitors read Hermann's own observations about crystal quality, circuit design, manufacturing precision. They saw photographs showing German engineers measuring components, testing circuits, recording data carefully. The exhibit made something unmistakably clear. German technical experts recognized American superiority. They reported it honestly. They grasped its significance. For direct comparison, the curators placed a German FUG-5 tank radio next to the American SCR-508. The contrast was stark. The German radio was heavier, larger, more complicated to operate, and inferior in every measurable performance category. It represented fine engineering constrained by manufacturing limitations. The American radio exemplified adequate engineering multiplied by industrial resources without limit. The exhibit notes explained the curators weren't celebrating American genius or dismissing German competence. Both nations employed skilled engineers who created effective equipment within their constraints. The difference wasn't intelligence, training, or theoretical knowledge. It was industrial philosophy and manufacturing capacity. Americans designed systems that regular, minimally trained users could operate reliably. Germans designed systems that brilliant experts could operate flawlessly. One approach scaled to global war, the other didn't. In a small glass case, the exhibit displayed a single radio crystal from that SCR-508. The crystal recovered from Tunisia was no bigger than a postage stamp, precisely cut quartz sealed in a metal container. The label noted that just this one crystal, 1 of 10 in each American tank radio, would have required approximately 40 hours of skilled German labor to duplicate. America had manufactured over 100 million such crystals during the war. That output alone would have needed every German radio technician working non-stop for 5 centuries. The exhibition attracted over 200,000 visitors during its year-long run. Some were veterans who'd operated those exact radios. Others were engineers fascinated by technology history. A few were military historians studying warfare from an industrial perspective. Everyone left understanding something deeper about how factories determine battles. Klaus Hermann died in 1997 at the age of 84. His obituary in the Institute of Electrical and Electronics Engineers Spectrum magazine acknowledged his contributions to radio technology, his wartime intelligence work examining American equipment, and his post-war role helping American companies learn from German innovations. The obituary highlighted something Hermann had insisted on throughout his life. Germany's defeat wasn't decided on battlefields. It was decided in factories. It wasn't soldiers who lost the war. It was production workers. It wasn't tactical mistakes. It was industrial capacity. His papers, donated to the Deutsches Museum in Munich, contained over 2,000 pages of technical reports, circuit diagrams, component specifications, and strategic analyses written between 1943 and 1945. Historians now possess detailed records of how German experts actually viewed American equipment and what they reported to Berlin's high command. One document especially stands out for its emotional power. Hermann wrote a personal letter to his wife in April 1945 as Soviet forces closed on Berlin. He'd sent his family to safety in Bavaria months before, remaining in the capital to complete final technical assessments until orders came to evacuate. In the letter, he described preparing to destroy classified documents and equipment to prevent Soviet capture. He reflected on 3 years spent analyzing American equipment, from that first SCR-508 in Tunisia to the latest radar sets captured during the Ardennes campaign. Every single example confirmed identical conclusions. America possessed far more than superior equipment. The entire American approach to warfare was fundamentally different. They'd industrialized everything, from radio crystals to entire armies, applying automobile factory and refrigerator production methods to military systems. Germany, Hermann wrote, had attempted an industrial war using craftsman's methods. German technology wasn't inherently inferior. In many fields, German theoretical knowledge surpassed American theory. But wars aren't won by theory. Wars are won by production. The nation that manufactures more tanks, more aircraft, more radios, more of everything will eventually defeat any opponent, regardless of skill or bravery. He ended with a prophecy. If another war came, it would prove even more industrial than the last. The victor would be whoever possessed the greatest manufacturing strength, the most advanced technology, and the capacity to produce precision components without limit. America had demonstrated exactly these capabilities between 1941 and 1945. Any future adversary would need to match or exceed American industrial power. Hermann believed no single nation could accomplish that. History validated his prediction completely. The Cold War that followed World War II became fundamentally a competition of manufacturing capability, technological progress, and production sophistication. The Soviet Union, despite vast natural resources and enormous population, couldn't match American electronics manufacturing, computer technology, or factory automation. That gap Hermann had identified in radio crystals in 1943 expanded to cover semiconductors, microprocessors, and integrated circuits. At its heart, the story of German technicians examining captured American radios is fundamentally about industrial warfare and the manufacturing revolution America experienced during World War II. It documents how warfare transformed from something primarily shaped by tactics, training, and courage into something determined by manufacturing capacity, technological sophistication, and production efficiency. Those radio crystals that impressed Hermann and his colleagues weren't magical. They represented precision engineering, absolutely. But more importantly, they represented precision engineering scaled to mass production. American industry had mastered something previously impossible at such enormous scale, manufacturing millions of units all to identical specifications. This capability, developed for radio crystals, extended throughout military equipment and eventually throughout every consumer product America produced. The lessons German engineers learned examining American equipment in Tunisia, Sicily, and Italy delivered harsh clarity. Superior individual equipment means nothing without quantity. Sophisticated technology fails if operators can't reliably use it. Theoretical perfection becomes worthless if manufacturing can't achieve it consistently. Only industrial capacity, properly organized and directed, defeats everything else. These lessons, purchased through Germany's defeat, became foundational to modern manufacturing philosophy. Design for production, build quality in, train operators effectively, support equipment adequately, scale to demand. The principles visible in American radio equipment in World War II now govern manufacturing in every global industry. The story beginning with Oberingenieur Klaus Hermann, opening that captured radio case in Tunisia in February 1943, concluded with fundamentally transforming how nations prepare for and conduct warfare. That radio crystal, a small piece of precision-engineered quartz, became symbolic of the Industrial Revolution in military affairs. It marked the moment when victory stopped flowing, primarily from battlefield prowess, and started flowing from factory output. German engineers analyzing American equipment understood this transformation while it happened. Their reports documented technical specifications, yes, but more importantly, they documented the end of one warfare era and the beginning of another. They witnessed, analyzed, and reported the future of conflict. That Berlin ignored their warnings didn't diminish their assessment accuracy. Today, the principles they identified: mass-producing precision components, factory automation, standardized parts for interchangeability, designing for manufacturability, form the foundation of every high-technology industry. The direct line connects radio crystals ground in American factories in 1943 to microprocessors produced in modern foundries in the 21st century. The industrial philosophy remains constant, only scale has changed. Those German technicians testing captured American radio equipment in 1943 weren't merely examining communication devices. They were observing the future of warfare, technology, and industrial organization. Their detailed technical reports, classified and filed during wartime, eventually became historical documents explaining not just why Germany lost, but how industrial capacity determines outcomes in modern conflicts. Their conclusion, expressed in technical language but unmistakable in meaning, was that Germany had challenged the planet's greatest industrial power with inadequate manufacturing capacity. That radio crystal, precisely ground quartz oscillator produced by American teenage factory workers in quantities Germany could never approach, conveyed the complete narrative. Industrial warfare requires industrial capacity. Without it, tactical brilliance, technological innovation, and individual courage cannot achieve victory. This lesson, learned by German engineers testing American radio equipment in underground facilities across occupied Europe, remains profoundly relevant today. In an era of microelectronics, satellite communications, and computer-directed warfare, the fundamental principle stays unchanged. Whichever nation possesses greater industrial capacity to manufacture sophisticated equipment in overwhelming quantities will ultimately prevail. Americans demonstrated that principle between 1941 and 1945, and the world continues adapting to what it means.